Now let us see some more applications of the intermediate value property. We start with the following problem. The question is as follows. Does there exist a continuous function f from R to R which has the following properties, such that if x is a rational number, that is x is in Q, then fx is an irrational number, that is it belongs to R minus Q. And if x is an irrational number, that is it is in R minus Q, then fx is a rational number, that is fx belongs to Q. So is the question clear? We are asking for, does there exist a continuous function from R to R such that if x is rational, then fx is irrational, and if x is irrational, then fx is rational. So we proceed with the problem as follows. Let us define a function g from R to R by the following rule. So what is g? I define gx equal to fx plus x for all x in R. And we are trying to give the contrapositive argument, that is assume that f is continuous. Okay, so I want to get a contradiction out of it, and then that will show that no such continuous function exists. So if I assume that f is continuous, then the first thing which follows is that g is continuous. Okay. Now in the following arguments I am going to use one thing time and again, that is this, that if x is a rational number, okay, and y is an irrational number, then x plus y is an irrational number. This is the observation which I am going to use time and again, which is very easy to see, because if x plus y is in Q, that means it is a rational number, then x plus y minus x, that is also in Q. So let us write it down. If x plus y belongs to Q, then y equal to x plus y minus x belongs to Q, which is a contradiction, simply because that sum and product of two rational numbers is a rational number. Okay, so this is the observation. If I use, then I get that sum of a rational number and an irrational number is always an irrational number. So this I am going to use in my arguments. Okay. Now if I have g is continuous, let us look at the property of g. Suppose x belongs to Q, then I know by the defining property of f that fx belongs to R minus Q. But then this implies, if I call this star, by star gx, that is equals to fx plus x, that is an irrational number, that means it is in R minus Q. So if x is rational, gx is irrational. But now let us take x to be an irrational number. Suppose x is in R minus Q. Then I know again that fx belongs to Q, but then this implies again by star that gx that is equals to fx plus x again belongs to r minus q. So it follows from these two calculations that G has the following property, that whatever x you choose in the set of real numbers, Gx is always an irrational number. So that means what I have is that G is a map from R to R minus Q, and G is continuous. That I am getting because I have assumed that f is continuous. Now let us see what more can I say about it. Let's try to use the intermediate value property on the function g. Okay? So let us take some a strictly less than b, where a, b both are real numbers. Then let us look at GA and GB. It can happen that they are same. It can also happen that they are not same. That means let us assume this. Now I know that GA and GB both are irrational numbers. Then what does intermediate value property say? Suppose I choose an x which lies between G and GB. So x lies between GA and GB. And let us choose x to be a rational number. That I can do, because if GA and GB are two unequal real numbers, then always there exists a rational number in between those two. By the intermediate value property, as G is continuous, by intermediate value property, which I will write as IVP, this means the intermediate value property, there exists y in R such that G of y is equal to x. Okay? But then you see, I got a contradiction, because gy is turning out to be a rational number because I have chosen my x to be a rational number. But look at the definition of G. It is a map from R to the set of all irrationals. That means for no x in R, Gx can be a rational number. But that has happened. And it has happened simply because I have assumed that GA is not equal to GB, which is not true then. So this is a contradiction, because G cannot take rational values, implies GA is equal to GB. What does this mean? Because I have chosen my AB to be arbitrary real numbers. So this implies then that G is a constant function. Okay, that means that is Gx is equal to a number C for all x in R. And surely she has to be irrational, and C is an irrational number. Now, since I have got that Gx equal to C, I got some inference about F also. Okay? Just writing down the definition of G, I get that Gx equal to fx plus x, that is equals to C for all x in R. and always remember that C is in R minus Q, that is, it is an irrational number. Then what do I know about F? That means Fx is just a line, that is, it is C minus x. Now in particular let me choose x equal to C by 2. Then I know that this is also an irrational number. This cannot be rational because if C by 2 is rational, call it R, then C equal to 2R. But if R is rational, then 2R is rational, that means C will be rational, which is not the case. That means C by 2 must be an irrational number. But then what happens to Fx? What is f of C by 2? That is C minus C by 2, that is equals to C by 2. Notice that C by 2 is an irrational number and f of C by 2 is C by 2, which is also an irrational number then. But you see that cannot happen. F takes rationals to irrationals and irrationals to irrationals. But in this case what is happening? F is taking an irrational number C by 2 to the same number C by 2, which is an irrational number, which is a contradiction. This implies F is taking an irrational number C by 2 to the same number C by 2. But that is contradicting the defining property of F. We said that F takes rational to irrationals and irrationals to rationals. So this is a contradiction. Which implies F cannot be continuous. That solves our problem. Okay. Now let us see another application of the intermediate value property. Let Px stand for a polynomial. We know how do polynomials look like. It is a0 plus a1x plus a2x square plus an x to the power n, and I say an not equal to 0. Let me assume an positive. Okay. Now I say that if n is odd, that means it is of the form 2k plus 1, then P has a real root. What does that mean? That means there exists some x naught in R such that P of x naught is equal to 0. Okay. What I want to do is I want to apply intermediate value theorem to the function Px, because I already know that any polynomial function is actually a continuous function. Okay. Fine. What I do first is I write Px as x to the power n times an plus an minus 1 divided by x plus a0 by x to the power n. The naive idea goes as follows, that if you look at this quantity here, if you take x large, does not matter in which direction, positive large x or negative large x, you feel that this quantity should converge to an, because all the individual quantities which are involved, they are having x in the denominator and that is getting large, so those quantities will be small. So you expect that the underlying portion converges to an, which is positive. Now since n is odd, if I take x positive, then anyway x to the power n is positive, but if I take x negative, then x to the power n is negative. That means you expect that there will be a change of sign for different values of x, and then 0 comes in between those two different values. That means by intermediate value property there should exist an x naught such that p of x naught is 0. That is the idea we want to use, but we have to make it rigorous. Okay, let us first write down what does it mean to say that the portion in the parenthesis converges to a naught. I say that given epsilon bigger than 0, I choose it in such a way that an minus epsilon is positive. I say there exists a real number k in R such that an minus epsilon is less than an plus an minus 1 divided by x a0 by x to the power n, which is less than an plus epsilon for all x in R such that mod x is bigger than k. That means the k I have chosen, it's a positive k, okay, k bigger than 0. This is just meaning of the fact that as x goes to infinity, the portion in the bracket converges to an. I have just written it in terms of epsilon following the definition of limit. Okay. Now if I choose x bigger than k, now if x is bigger than k, what happens then? Then an minus epsilon times x to the power n is anywhere less than x to the power n times an plus an minus 1 by x plus a0 by x to the power n, which is less than an plus epsilon times x to the power n. Notice then that by my choice this also happens, because an minus epsilon is positive. I have taken my x to be positive, so that is also bigger than 0. Now what I can do is, suppose I choose x less than minus k. That means now I am choosing my x to be negative. Notice that since I have taken my n to be odd, x to the power n is also negative if x is negative. So what does this imply? This implies that an minus epsilon times x to the power n is bigger than x to the power n times an plus an minus 1 by x plus a0 by x to the power n, which is bigger than an plus epsilon times x to the power n. Now notice that as x is less than minus k, that means x is negative, then x to the power n, x less than minus k implies x to the power n is strictly less than 0. This implies, now since x is less than minus k, it implies that x to the power n is also strictly less than 0. That implies what? It just implies that x to the power n into an plus an minus 1 by x plus a0 by x to the power n, this is less than x to the power n times an minus epsilon, which then is strictly less than 0. So this implies what? It implies that if x is bigger than k, then px is bigger than 0. If x is less than minus k, then Px is less than 0. Now this implies then there exists x naught in R such that Px is equal to 0. Why so? Because there is one value of x for which Px is positive, there is one value of x for which Px is negative. That means 0 lies between those two values, and hence by intermediate value property there exists an x naught such that P of x naught is 0, and this implies that x naught is a real root, which is exactly what we wanted to prove. Now we are going to start with a concept called uniform continuity. This is a concept which we will interact while talking about Riemann integration of continuous functions. That is the sole purpose of introducing this concept now. So first what we will do is we will start with an example of a function and check the epsilon delta definition of continuity. So let us look at this function fx equals to 1 by x square, where x belongs to open 0, infinity. Okay. I certainly cannot include 0 in the definition because 1 by x square will not be defined then. What I want to check is first that this function is continuous at every point of 0 infinity. And to do that, what I will do is I will just try to show that given epsilon there exists a delta. I want to see how do I find out deltas, okay, and how does delta depends on epsilon, x or whatever. So choose a point x equal to x naught to check continuity at x naught. So how are you going to do about this problem? I first look at the quantity fx minus fx naught, and then just I write down the definition of f. So that is modulus of 1 by x square minus 1 by x naught square, and then if I expand it, what I get is mod of x minus x naught times x plus x naught. I am not putting modulus here because both x and x naught are positive, divided by x square times x naught square. Now let's assume that x satisfies the inequality x minus x naught is less than x naught by 2. That is, x belongs to x naught divided by 2 and then thrice x naught divided by 2. That is a choice of neighborhood. But if I have this, then what I have is that mod of x, that is equals to mod of x minus x naught plus x naught, and then I use triangle inequality to get x minus x naught plus x naught, but x minus x naught according to my choice is less than x naught by 2. So this is less than x naught by 2 plus x naught, which is equals to thrice x naught by 2. Okay, and then this implies that mod of x plus x naught by triangle inequality is lesser equals to mod x plus x naught, but mod x is less than 3x naught, so this is less than thrice x naught by 2 plus x naught, that is 5x naught by 2. Now if I start with mod x naught, which I can write as mod of x naught minus x plus x, and apply triangle inequality, that is x naught minus x plus x, which then is strictly less than what was the estimate on x naught plus x? Let us see. X naught plus x is 5x naught by 2. What I do is I look at x naught minus x plus mod x, but mod of x naught minus x is less than x naught by 2. So what I have is, here I have mod x naught by 2 plus mod x. Actually many of those mods are unnecessary because x and x naught are positive. Anyway, this implies then that mod x is bigger than x naught minus x naught by 2, which is equal to x naught by 2. Now I want to use all these informations in my estimate, that is mod of fx minus fx naught, which I know is mod x minus x naught into x plus x naught divided by x square times x naught square. Now I am going to use the above estimates. What I get first is that this is less than mod x minus x naught. I am going to do anything with it. I will just keep it in the above form, and I know x plus x naught from the previous work that it is less than 5x naught by 2, and in the denominator what I am going to use is that mod x is bigger than x naught by 2. That means 1 by x square is less than x naught square by 4. So what I am going to use here is x naught square by 4, and there is one other x naught square remaining here. Okay, what I get then is that this is mod x minus x naught, which is intact, times 10 divided by x naught cube. All now I want is, given epsilon, we want mod of x minus x naught times 10 by x naught cube to be less than epsilon. If I want to have this, this implies we should have mod of x minus x naught is less than epsilon into x naught cube divided by 10. So now what is the delta I am going to choose? Certainly the choice is obvious. I choose delta equal to the minimum of x naught by 2 and the quantity epsilon x naught cube divided by 10. Now the point to note here is that the delta which I got, whose precise expression I have now here, it involves x naught, at the same time it involves delta. That means given epsilon, when you want to choose delta, it depends on epsilon and the point x naught where you are checking the continuity of the function. Okay. Now notice one more thing, that when I get my x naught to be small, that implies that this minimum which is appearing, that will also be small. So let us note it down. From the previous expression, it follows that for fixed epsilon but small x naught, a smaller delta will work this is what I got analytically. But I want to see it from the pictures. Is that possible? Let us try to draw the picture. So this is the y-axis. This is the x-axis. I have 0 here. Let us try to draw the curve of fx equal to 1 by x square. So it looks something like this. Okay. Now first let us choose the point x naught here. This is my x naught. And I take a fixed epsilon. Now here I have my fx naught. Here is where is my fx naught. Now notice that if I choose an epsilon band around fx naught, this is fx naught. An epsilon band, how does that look like? Let us say it is here, it is here. That means I want a choice of delta such that fx lies in this band. Then the obvious choice is you put this down, you put this down. It seems this delta, this kind of a neighborhood of x naught will work, for which I will get delta. Now let us draw another copy of this picture. This is the y-axis, this is the x-axis. The graph of the function looks like this. Okay. Now let me choose x naught here. Okay, that means I have chosen a smaller x naught. Then the corresponding, this is my fx naught. Okay, it is much higher. That is obvious, because if x naught is small, then fx naught has to be big, because it is 1 by x naught square. Now I choose an epsilon. Let me choose an epsilon around this, which is the same epsilon which I have worked. So in the picture it will look something like this, the same epsilon band. Then what should work as delta? That means you just have to project it down below, that is somewhere here, and here you will get somewhere here. That means this is now your neighborhood. See, the length of the neighborhood is this much. Here the length of the neighborhood was this much. So it follows from the picture, if my drawing is perfect, that for this smaller x naught, the delta is getting small. That means delta does depend on x naught. But that might be because I got delta because of my sloppy argument. Analytically, I need to prove that there is not a single delta which will work for all x naught bigger than 0 for this function fx. So in the previous example, it seems that if I give you a epsilon, then the delta which you are going to get, it depends on epsilon as well as the point x naught. Uniform continuity means that this does not happen. That means delta can be chosen independent of x. So the precise definition is as follows. Suppose I have a function f from domain of f, that is a subset of real line, to R. Then f is called uniformly continuous on domain of f if given epsilon bigger than 0, there exists a delta bigger than 0 such that whenever mod of x minus y is less delta for x, y in domain of f, then mod of fx minus fy is less than epsilon. That is, you take any 2 points xy such that mod of x minus y is less than delta where x and y are in the domain of f, then mod of fx minus fy is always less than epsilon. So the thing to note is, first of all, that uniform continuity deals with domain of f. It is not about points, it is about a set. This is number one. Number two is an easy exercise which you can easily check, that if f from domain of f to R is uniformly continuous, then f is continuous on domain of f. Okay. Now what I want to show you is that the function which I started with, fx equals to 1 by x square, defined on 0 infinity, is not really an uniformly continuous function. That means there exists an epsilon for which no delta works. So let us try to see that next. So the example, later we will see an easy proof of this. I look at the function fx equals to 1 by x square, where x belongs to 0 infinity. Okay. I say, given epsilon equals to 1, let us choose a delta naught which works for some x naught. Okay. Now I am going to choose an x1. I would show that the same delta naught does not work for x1. So what I do is I choose x1 equals to delta naught by 2, and I choose x equals to delta naught. Then modulus of x1 minus x, that is delta naught by 2, which is strictly less than delta naught, and then modulus of fx1 minus fx, that is modulus of 4 by delta naught square minus 1 by delta naught square, which is 3 by delta naught square, that is bigger than 3, as delta naught is less than 1. This implies mod of fx minus fx1 is not less than epsilon. This implies the function fx equals to 1 by x square is not uniformly continuous on 0 infinity. But let us do some more experiment with this. I again look at this function fx equals to 1 by x square. And now let me assume that x is bigger than or equal to a, which is strictly bigger than 0. And now I can show that this function is uniformly continuous. What does it show then? It actually shows that the concept of uniform continuity depends on which domain of f you are working with. So let us see why is this uniformly continuous. So I look at mod of fx minus fy, that is mod of x minus y into mod of x plus y divided by x square into y square. Okay, fine. That means I have to find a delta which works for all xy and a given epsilon. But since x and y both are bigger than a, what I get is that this is lesser equals to mod of x minus y into mod of x plus y divided by a to the power 4. Okay. Now if I can somehow show that mod of x plus y divided by x square y square is bounded on a infinity by a constant m, then what I get is that mod of fx minus fy is less or equals to m times mod x minus y. If I can show that, then this implies that given epsilon bigger than 0, choose delta to be equal to epsilon by m. Now notice that this delta is not depending on x and y, because if I choose my delta to be less than epsilon by m, this would imply mod x minus y less than epsilon by m implies mod of fx minus fy is less than or equal to m times epsilon by m, which is epsilon. So all we need to show is that this quantity is bounded by some constant m which is independent of x and y, but that is pretty easy. I just write mod x plus y divided by x square y square as these mods are actually unnecessary because I am working with positive x and y anyway. Then this is 1 by xy square plus 1 by x square y, but as x bigger than or equal to a and y is bigger than or equal to a, what I have is 1 by xy square plus 1 by x square y is lesser equals to 1 by a cube plus 1 by a cube, which is equals to 2 by a cube, which I can take to be equals to my m. So this implies that mod of fx minus fy is lesser equals to 2 by a cube times mod of x minus y. That means my choice of delta actually is a cube epsilon divided by 2. See, delta depends just on epsilon, not on the points, but certainly it depends on the set. Notice that if I had taken my a to be equal to 0, that was 0 infinity which I wanted to work with, then my delta will be 0. So close to 0 I have got a problem, but away from 0, if the function is defined for x bigger than or equal to a, then it quickly becomes uniformly continuous. Okay. Now we come to the most important theorem of uniform continuity and why we wanted to do it. We have seen that if I have a uniformly continuous function, then the function is always continuous. We have also seen that there exist continuous functions which are not uniformly continuous. For example, fx equals to 1 by x square on open 0 infinity. That is a continuous function certainly that I have checked, but it is not uniformly continuous. But there are certain domains on which continuity always gives me uniform continuity, and that is what I am going to prove now. So that is a theorem. Let f from closed interval ab to r be a continuous function. Then f is uniformly continuous. That is, the statement of the theorem says that if I have a continuous function defined on a closed interval, closed and bounded interval, then the continuous function actually is uniformly continuous. Okay? So let us try to prove this. The proof actually uses the contrapositive argument. So let's assume that f is not uniformly continuous. Assume that f is not uniformly continuous. What does this mean? Some function is not uniformly continuous. It means there exists an epsilon for which no delta works. The definition of uniformly continuous function says that given any epsilon there is a delta satisfying some inequalities. It is not uniformly continuous then means that there exists a rogue epsilon, that means there exists an epsilon for which there is no good delta. So let us just try to write it down. It implies there exists epsilon bigger than 0 such that given any delta bigger than 0, there exist 2 points which I will call x delta and y delta in the closed interval AB, such that mod of x delta minus y delta is less than delta, but modulus f of x delta minus f of y delta is bigger than or equal to epsilon. That is what not uniformly continuous means. Fine. So with respect to this bad epsilon, I am going to choose delta according to my will. So I will start choosing delta equal to 1 by n. Then corresponding to this delta, there are 2 bad points, x delta and y delta, which now I will call xn and yn. Then there exist xn in AB and yn in AB, such that mod of xn minus yn is less than 1 by n, but mod of fxn minus f of yn is bigger than or equal to epsilon. Okay. So the thing is, I have got hold of 2 sequences. One is xn, other is yn on the closed interval AB. But I don't know anything about convergence of those sequences. But see, I am on closed interval AB and I know Bolzano-Weierstrass theorem. It says that given any sequence in the closed interval AB, I have got a convergent subsequence. So let us consider a convergent subsequence of xn and call it xnk. So by Bolzano-Weierstrass theorem, there exists a convergent subsequence xnk of xn, and let xnk converges to x naught, which is also in closed interval AB. But since f is given to be continuous, I know that this implies f of xnk converges to f of x naught. Also notice that mod of xnk minus ynk, that is less than 1 by nk. What does this imply? It implies xnk minus 1 by nk is less than ynk, which is less than xnk plus 1 by nk. Apply sandwich theorem now. This converges to x naught, this converges to x naught. This implies ynk also converges to x naught. Then again by continuity, this implies that f of ynk converges to f of x naught. But then this implies that f of xnk minus f of ynk, that converges to fx naught minus fx naught, which is equal to 0. Okay. But if you look back, the condition on fxn and fyn was this, that it is bigger than or equal to epsilon for all n But in that case, it cannot happen that it has a subsequence which converges to 0. But that is what I have got here, which is a contradiction. This happens because I have assumed that f is not uniformly continuous. So it follows that f is uniformly continuous. Now let us ask the following question. Suppose f from domain of f to R is a continuous function, and let xn be a Cauchy sequence. The question I want to ask is, look at the new sequence f of xn. Question is it Cauchy? That is, the question you are asking is that suppose I have given you a continuous function, then is it true that it takes a Cauchy sequence to a Cauchy sequence? The answer is no. Answer is no. Well, I look at this function fx equals to 1 by x square, where x belongs to 0 infinity. I look at this sequence xn equals to 1 by n. Then this sequence is contained in domain of f certainly, and also is a Cauchy sequence. But then what is f of xn? F of xn is turning out to be n square, which is an unbounded sequence. And if you remember, we have proved that the first thing a Cauchy sequence does is that it becomes a bounded sequence. But this is an unbounded sequence, so it cannot be Cauchy. So f of xn is not a Cauchy sequence. So in general, it is not true that a continuous function takes a Cauchy sequence to a Cauchy sequence. But I am going to show that if my function is uniformly continuous, then it does take a Cauchy sequence to a Cauchy sequence. So let us try to prove that. This is a theorem. So let f is from domain of f to R be uniformly continuous. If xn is a Cauchy sequence, then the new sequence fxn is also a Cauchy sequence. Okay, the proof is very simple. If I have to show fxn is Cauchy sequence, what I have to do is, so to prove that, given epsilon bigger than 0, there exist capital N such that for all mn bigger than or equals to capital N, mod of fxm minus f of xn is less than epsilon. Now using uniform continuity of f can get a delta corresponding to the given epsilon, such that if mod of x minus y is less delta, then mod of fx minus fy is less epsilon. That is the definition of uniform continuity. But notice that xn is Cauchy. So thus there exists capital M such that mod of xm minus xn is less than delta if mn bigger than or equals to m, by the fact that xn is Cauchy. Okay. But then by definition of uniform continuity, mod of fxm minus fxn is less than epsilon for all mn bigger than or equals to the same capital M. But this is precisely what I wanted to prove here, that given epsilon bigger than 0, there exists n such that for all mn bigger than or equals to n, mod of fxm minus fxn is less than epsilon. See what I have found out. I found out that mod of fx minus fxn is less than epsilon for all mn bigger than or equals to m. That means the stage which I called n in the previous case, I found it to be m. And what is this m? This m works for the delta in the Cauchy sequence xn. So this proves the result. Now using this, it follows quite easily that the function fx equals to 1 by x square is not uniformly continuous in 0 infinity. Let us see how so. I look at the function fx equals to 1 by x square. Let me take x in even 0, 1. There also it is not uniformly continuous. If f is uniformly continuous, then xn Cauchy implies fxn is Cauchy, right? But that is not the case. Let me look at the sequence xn equal to 1 by n, which I have looked at earlier. If xn equals to 1 by n, then xn is Cauchy. But f of xn equals to n square, which is not Cauchy. But my previous theorem says that if f is uniformly continuous, then a Cauchy sequence will be mapped to a Cauchy sequence by f. I have assumed my f to be uniformly continuous on 0, 1, and I can see that there exists a Cauchy sequence 1 by n which is not getting mapped to a Cauchy sequence. That means f cannot be uniformly continuous. So now then we have an easier proof of the fact that the function fx equals to 1 by x square is not uniformly continuous in 0 infinity. Earlier we have established the same fact using the epsilon delta definition of uniform continuity, but here we have an alternative proof using the definition of uniform continuity.